All right, here's our video just continuing this series of the acid-base properties of salts and conjugate pairs. So a lot of this is very introductory stuff, and then there is some more high-level stuff that's going to come down a little later. So starting with some of the introductory stuff, we're just asked for net ionic equations that show hydrofluoric acid behaving as a Bronsted-Lowry acid. So HF is going to mix with H2O, and it is going to dissolve into F minus and H3O plus, because the definition of a Bronsted-Lowry acid, or acid, is it is a proton donor. It is going to give away its H plus. The definition of a Bronsted-Lowry base is that it is a proton acceptor. It is going to accept an H plus. My conjugates, I have a conjugate base here that is ready to be a proton acceptor. And I have a conjugate acid here that is ready to be a proton donor. So hopefully that one is pretty straightforward for us at this point. Section 2 gets into identifying whether each species is a Bronsted-Lowry acid or base in an already existing net ionic equation. So the first thing I do is I see NO2 minus. It has a negative charge and it has no H, which are two clues that this is going to act as a base. It is likely to attract a proton towards itself. H2SO3, on the other hand, has an H, so it is likely to act as an acid since it may give one away. On the flip side of that, the conjugate acid of NO2 minus is going to be HNO2, which is an acid. Specifically, it's a conjugate acid in this. Really, it just acts as an acid. And H2SO3 gives away one of its H's and becomes HSO3, which acts as a conjugate base. This is really an amphoteric species because it could accept another H and become H2SO3, or it could give away another H and become SO3 2 minus. Either of those are going to work, and that's kind of the definition of amphoteric species. Moving on to section 3, we have a formula-based one. So A, we're given a formula of something, and we're asked what the conjugate base of that thing is. So if we're asked what the conjugate base is, that means we're basically asking, what is this thing after it loses a proton? Because acids lose protons, they donate protons, and then they become conjugate bases. So if I lost a proton from that, I would become C2O4 2 minus. On the flip side, the formula for the conjugate acid of HS is basically asking what would happen if this base gained a proton. So if it gained a proton, it would become H2S, because a conjugate acid is going to form after a base gains a proton. Next, we're going to skip ahead a bunch of sections to section 12, where we're writing a little bit about conjugate acid formulas. So we're told the nitrite formula is the nitrite ion is the conjugate base of the weak acid nitrous acid. And we're given the Kb value of nitrite, the ion, is 2.2 times 10 to the negative 11th. And then we're asked to write the equation for the reaction that goes with this equilibrium constant. Okay, so the first thing I want to do is write a dissociation for my nitrous acid, even though that's not necessarily my answer. So I have my nitrous acid interacting with water to form, sorry, I wrote that out of order. Not that it really matters, but I like to write it in this specific order just for consistency's sake. It's going to form those two products. And then I'm asked for my equilibrium constant for my nitrite ion. So my nitrite ion then is going to interact again with the water. And it's going to kind of go back and form OH minus. Okay, so this is my reaction for my equation that goes with the equilibrium constant associated with NO2 minus. I really didn't have to write that first part, but I chose to. Section 13 is pretty similar. Section 13, I'm given a compound methylamine and told that it's a weak base when dissolved in water. And I'm asked to write the Kb expression for the weak base equilibrium that occurs in an aqueous solution of methylamine. So again, what I'm going to do is I'm going to write out my methylamine interacting with water. And since my methylamine is a base, it is accepting a proton, making it H3 instead of H2. And my H2O is acting as the acid, donating a proton. My base accepted a proton. And so that is going to be my Kb expression. If I wanted to solve for Kb, I could then, go in and write out my formulas here, but that's not really what I'm asked to do. I'm just asked to write the full expression. So I'll stick with that. Next, we're going to skip ahead another few sections and go into section 17, where we're writing the net ionic equation for the acid-base hydrolysis equilibrium that is established when ammonium perchlorate is dissolved in water. So the first thing I want to do is figure out what the heck is ammonium perchlorate. Well, it's NH4 ClO4, which is an ionic solid. It's made from a cation and an anion that are ionically bonded together. And so if I dissolve this ionic solid in water, it's going to form ammonium and chlorate ions. Ammonium is the conjugate acid of a weak base, NH4OH, or ammonium hydroxide. Weak base. Chlorate is the conjugate base of a strong acid, HClO4, strong acid. What that means is that A, my solution is acidic, and B, I'm going to focus on my ammonium ion because I want to focus on the thing that came from the weak conjugate. Okay, and that's true for most of these types of equilibriums, all these types of equilibriums, really. So I take my ammonium, NH4+, I add it to water, and that is going to form hydronium, and it's going to form its conjugate base of NH3. I've been forgetting states of matter a lot here. They are important for me to write. So when we dissolve ammonium perchlorate in water, we get ammonium and we get perchlorate. The perchlorate stays in solution, so we don't need to worry about its interaction with water because its conjugate is strong. It dissociates completely. The ammonium does not stay in solution because its conjugate is weak, and so we do need to worry about its interactions with water, in which case we are going to see that reaction happening, and so that is our acid-base hydrolysis equilibrium. We can do another one of those because they're a little bit tricky at first, but you get used to them eventually. This time we have calcium hypochlorite. So calcium hypochlorite is CaClO2. When we dissolve that, we would get calcium ion and 2 chlorite ions. Calcium is the conjugate acid of a strong base. Chlorite is the conjugate base of a weak acid. That means our solution is going to be basic, but we want to focus on the weak ion here. In this case, it's the anion. Why do we focus on that? Because these are all staying in solution because they come from a strong base. These are not, so they influence our equilibrium. So we take our ion, hypochlorite. We write it interacting with water. And we see what happens. It acts as a proton acceptor to form HClO. And water acts as a proton donor to form OH minus. Okay? Hopefully after 2 of those, we're kind of getting the hang of it. And if not, I think section 18 is a really good way of practicing how we can see those strong, strong, weak, strong interactions. So we're going to indicate whether each of the following compounds will give an acidic, basic, or neutral solution when dissolved in water. So ammonium chloride will dissolve into ammonium and chloride. Let's say that ammonium formed NH4OH and the chloride formed HCl because that's what their charges tell us they're likely to do. NH4OH is a weak base. HCl is a strong acid, so that means this solution will be acidic. Strong acid outweighs the weak base. Next, calcium chloride would form CaOH, which is a strong base. Chloride would form HCl, which is a strong acid. So this is going to be neutral, strong and strong. Barium bromide comes from BaOH2, a strong base, and HBr, a strong acid. So since that's strong, it will also be neutral. And lastly, barium iodide comes from BaOH, a strong base, and Hi, a strong acid. So that too will be neutral. We had a bunch of those that created neutral ones. Let's just do one more for the sake of it. Let's say we had calcium cyanide. Calcium cyanide comes from a strong base and a weak acid. Therefore, this would make a basic solution. So hopefully, as long as we have our strong acids and bases memorized, those become pretty easy to do. All right, I think with that, we should be good on this section of ALS. If you need more practice, you can try those, but I think they should be pretty easy for us. Oh, I actually just did all those. This is just a duplicate slide. So we can move on to our future sections of ALS. Thanks.